This is lecture 6, part B, and what we're going to do is continue on our discussion of register transfer notation with pretty much some example data operations which shows transfer of data. And we'll get into a few examples as well. So register transfer notation, register transfer language, it's kind of a highly abstracted way to describe digital circuit. Typically we use it quite often when describing computer circuits, and let's see some examples here. So here's a quick example, and what it's saying there is the data is transfer in R2 is transferring to the data in R1 if this signal is asserted. So the notion here is that it doesn't really say it directly, but you can infer it from the statement that R1 and R2 are registers, and by the way it's written, C1, and C1 is a control signal. So typically that loading is going to happen when C1 is asserted and a clock edge comes around. Now this RTL never puts a clock in there. Everything's understood to be synchronous. If it's not synchronous, it's actually kind of quite hard to represent an RTL. But this is the resulting circuit. You can see that, hey, I have two registers, one register, two register. R2 data is feeding into R1, which is there's the connection. And what else here? Something is going to control the loading of R2 into R1. So I connected this C1 signal to the load input on the R1 register. So that's the cool thing about this, is that this RTL essentially implies this circuit, but it works in both directions. I can give you a circuit like this and say write some RTL for this circuit, and you could come up with this equation here. Now the associated timing diagram is these things are certainly synchronous. You get a see a rising edge here. So when C1's right here on the rising clock edge not asserted, it doesn't load anything. It waits till this clock edge when C1 is asserted that the load of this data on A, here's A right here, gets loaded into the register R1. So here's B. B is the output of R1. This should have put that in there, R2, R1. Anyway, so this is a quick example showing that transitions are synchronous. They're just registers as you know and love them. Never write a clock signal in an RTL statement. So this is a quick example here. We'll do some more examples later of, hey, here's the RTL statement, draw a circuit. Now the issue is like these problems, I know people have some issues with them, but they're actually pretty straightforward problems, knowing that we're always working with registers. So this problem, I mean, what is it? It practically does itself for you. The issue here is, let's draw this thing. I see two registers there. I'm going to draw two registers. I'm going to call one R1, one R2. And so what happens here, what it says is there's a path from R1 to R2, and there's a path from R2 to R1. And these would be the data inputs. Also on these things, this transition of data is going to happen when the load signal is asserted. So I'll put a load signal on these also. And I am going to call that done. So another thing to notice in this circuit is there's really no notion of data widths on this thing. It's sort of implied. Certainly you couldn't, when you do your circuit, you can toss in your data widths on this. Okay. So there's a ton of data transfers out there, and so this section is completely arbitrary. What you want to indicate to anyone reading your ITL is just to give them an idea of what you're doing in the circuit. Now, these RTL is not like a science. It's not syntactically checked or anything like that, like a programming language or HDL. What you want here is just to be able to transfer information to people. So when you're writing RTL, certainly there's no putting like a comment on there to let people know what you're doing. Okay, so these are just basic transfer operations. By the way it's written here, the transfer to R1 to R1 is unconditional, and this, I guess you could call this a hold, because R1 is transferring to R1. This one would be R2 transfers R1 when C1 is off, which essentially makes C1 a negative logic signal. Oftentimes you see RTL that looks like this, so there's a question there. Is that an OR or an addition? People wouldn't know unless you told them, and so you would have to put a comment on there saying, hey, it's addition. This is a standard operation here that looks like addition, right? Under some condition here, I don't know. But this is actually, if you think about it, this is what a counter does, and this is a typical increment operation. So technically I could throw a ripple carry adder in here and model it like that, but it's better that I notice it's simply doing an increment and using a counter to implement this RTL. So anyway, additionally here we can see a counter being incremented, and also a counter being fed into another diagram. So I think that's worth drawing. There's my two registers, and what it's saying is there's a path from R1 to R2. So once again, this is a counter here. It's going to have an up signal on it. It looks like the up signal is always on, and we'll say this has a load signal with a C in. Okay, the issue here is what I wanted to do with this example is say that this counter can increment at the same time as the output of that counter is loaded into R2. So R2 gets loaded with an R1 value, not the incremented R1 value. So this is an example of multiple operations, we'll say multiple micro operations happening simultaneously. The tendency is to think that R1 plus 1 is what gets loaded into R2, and it's not. So these are general logic operations. This is just and, or, inversion, nothing big here. The notion here is we also have shift lefts and shift rights. So this is essentially taking a register and shifting it right. This is taking a register and shifting it left. And so I put in this extra notation. That means I'm shifting it left, but on the right side I'm stuffing in a 0. So it's not really clear when I'm shifting this thing right what I'm putting in on the left side. If that's important, then you'd put that in a extra information in a comment. So these are standard shift operations. Once again, you're shifting left or right. So this is a shift right. And so there's a notion of what gets stuck in there. And so that's why in some of this notation here, I actually called out the value to put in that thing. So this is just a notation I made up. Certainly you can make up your own notation on this. One of the classic functions out there is a rotate. When I do a shift, I actually lose a bit. And so with the issue with the rotate, I actually, like this is a rotate right. So everything gets shifted in the right direction. That LSB comes around and becomes the MSB for rotate. So we had a rotate left, rotate right. It's really quite interesting. RISC-V doesn't have rotate instructions. They have shift instructions, and I'd say most microcontrollers, most instruction sets do contain rotate instructions. So there's two types of shift operations, just simple shifts as we noticed them before, but there's also, we'll say, barrel shifts. So a typical shift operator it's kind of under our shift register. It's understood to shift one bit at a time, but we don't really need to do that. We can actually shift multiple bits. So if I'm shifting multiple bits on the same clock cycle, it's referred to as a barrel shift. And it turns out the shift operators in RISC-V are actually barrel shifts. The other notion here is arithmetic shifts, and these shifts are shifts that protect the sign bit. So an arithmetic shift, this happens to be arithmetic shift left, I retain the sign bit, and it's actually this bit that I lose. So you can see that these bits are the ones that are shifting over in this arithmetic shift. Now the same thing, I don't have an example for it. When you're shifting right, essentially the sign bit is propagated towards the right direction. So the new bit is always the sign bit. The sign bit's protected, but the new bit on the left side when I'm shifting right is the sign bit.